So, is my microphone working? Seems to be okay. So it's very nice to be here today. I think Matsumoto-san said everything I have to say. So are there any questions? No. But he did make some very important points that I hope I can help emphasize during my time here. One of them is that systems are becoming more complex and much more interconnected. This puts a burden on all of us in the software engineering community to raise our capabilities, to think more at the systems level to address all the issues that come with building big software systems. The fact is that this is a very challenging job. Okay? We need to make software that does all the functionality, brings all the capabilities that it can bring to our customers, to our governments, to the consumer. And yet at the same time, we need to make sure it's engineered well so that it's safe, secure, and has longevity, that it can work into the future. As you know, it's very hard to build large software systems. And so if we don't build them in a way that they can evolve into the future, then we haven't done our job very well either. So one of the great themes of today for all of us as software engineers is to think at that systems level about all the problems that we have, to learn how to abstract our thought, to figure out how our system's going to work not only across all the functions it does, but across all the time that it will exist. Now, I also heard the nice comment about the typhoon. It's very good that the typhoon has passed us by. I've been in Japan now for 3 days and experienced the typhoon and a small earthquake. So I'm getting the full Japanese experience while I'm here. But the people here have been so warm and received us so well as we go around to talk about the issues of software. Another thing for all of us to be aware of all the time is that the challenges of the software engineering community are challenges that the global community faces. So we need to come together as a global community to meet these challenges. The challenges of reliability, of assured software, are not challenges that will be overcome, that will be satisfied by any one organization or few people. It will take the combined efforts of all of us, of SEC, of SCI working together, as an example, to meet these challenges and advance the state of our art of software engineering. Okay, let's see if I can work this here. Oh, no, that's not working. Oh, this is just a pointer. Yeah, that's why it's not working. So I can do that, yes. So as a starter, we have to understand that much of the software that is out there today contains a lot of security vulnerabilities. This is not good. This does not represent us as software engineers very well. A recent study by the SANS organization, which is another organization in the United States that looks at things like security, has found that in a representative sampling of installed software, almost 70%, 69%, almost 70% of this installed base of software contained the 25 most dangerous software coding errors, errors that lead to vulnerabilities in the code. Typical, this is like buffer overflow, cross-site scripting, those types of errors. Errors that, by paying attention to quality, we could actually eliminate or reduce dramatically. Now, the issues of software and software security will still remain if we eliminate these common errors. But it will make our problem a little easier to address. It will allow us to address the most complex and advanced threats and not worry about the vulnerabilities that come just from software coding errors. So this is a very important thing for us to start to address in our profession just as mechanical engineers addressed common errors in bridges and buildings to try to make them more secure and more assured when they built them. We need to bring the software engineering community into the same state of maturity that mechanical engineers, electrical engineers, aerospace engineers have found themselves. We are a young science, and so we have some reasons why we're not quite as advanced as these other disciplines, but it's not really an excuse. It's just a reason. And we need to overcome the immaturity of our profession as we go into the future. As some examples of how security can start to affect all of us, many of you know that just a few months ago, there was a lot of news about the Heartbleed bug, a bug that existed in a piece of software that did open SSL connections. It was an open source software and used by many people throughout the world in the financial industry for securing credit card information and such, and for other reasons as well. And although the theory of open source software is that there's so many eyes on this software that all the defects will be found by the good people looking at this software, in actuality, most people adopt this software without getting very deep into the particular implementation of the software. And so the bug that was in Heartbleed, OpenSSL, proliferated throughout multiple systems around the world. And it rested there for over 2 years and was beginning to be exploited before everyone discovered it. SEI worked really hard on this to help the community respond to this and to make the corrections to their software that would secure the OpenSSL modules. But it had big implications across the internet. And I'm sure it had some effect here in Japan as well. The idea was that if you used OpenSSL, you thought your data was secure, and yet in reality, your data wasn't secure to certain attack. One thing we read as we were preparing for our meeting here is that I think in the year that ended in March of 2014, about 180 million yen had been lost on online banking in Japan in 1 year. And in April of 2014 alone, as people understand how to attack the system more, almost 200 million yen were stolen in online accounts in Japan. This is usually done by stealing both the password and usernames from people. And this, unfortunately, my father was a small businessman, so I have a certain empathy and sympathy for the small businessmen around the world and the wonderful things they do. Unfortunately, online banking often is used by small businessmen and women in Japan. And through various techniques of stealing passwords, maybe it was a spam attack, what we call spear phishing attack, to get the people to identify and reveal their password and username. 200 million yen, $2 million worth of money was stolen from various small business people. This can, as you know, can cause a small business to fail. So it has implications beyond just an irritant. It can really affect a person's livelihood. And so we worry about that every day. And we know even in large organizations like JP Morgan Chase, cybersecurity attacks are becoming more prevalent, more dangerous, and having more impact. Now, aside from these attacks that are trying to steal money, across the world, there are persistent campaigns of advanced cyber hackers that are attacking both governments and companies. And they're doing this usually not just to take money, but to get information. Maybe it's government information. Maybe it's intellectual property that belongs to a company. As you know, companies throughout the world spend a lot of time doing research and development to develop intellectual property that hopefully gives them an advantage in the workforce, in the marketplace, that allows them to compete globally. And through concentrated efforts by some governments in the world, there have been many attacks now of very sophisticated hackers trying to gain the intellectual property that these companies have spent lots of time and money on, to sort of short-circuit the advances of companies in these other countries. It's been estimated in the United States that $1 trillion of intellectual property was stolen last year. $1 trillion. 100 trillion yen of value by advanced persistent threats. So often when we talk about advanced persistent threats, we think of only the government-to-government hacking that goes on. But in fact, a lot of this is not government-to-government. It's government on industry, government on whole domains of industry, like attacking the banking system or the aeronautics system in the countries, the aeronautical industries in countries, so that another country can start to build its own aeronautics industry. And I'll leave it to you who that country might be that's been doing that. I think we all know who that country is. In the US, we recently had, right before our holiday season in 2013, one of the large retailers in the United States is Target, a department store, a retail store. It sells clothing and other materials. And through a vulnerability in their systems, a vulnerability that was actually introduced not by the Target system itself, but by the system of one of Target's subcontractors that had rights inside the Target system. This subcontractor system was penetrated, and it led to the theft of, I think it's something like 40 million credit card names, PIN numbers, and other information that could be used on the internet. Immediately in 2013, just in that fourth quarter of 2013, just in the few weeks before our big holidays, this cost Target $61 million in revenue. And the reputational damage was even worse because people don't have confidence in shopping at Target right now. They believe that the reputational impact, as well as some of the remedial efforts that Target has taken to make sure that people's personal data has been secure, could end up costing the company $8 billion, 800 billion yen roughly. You can see how an attack like this could destroy even a large company. It could bring a large company down. So you could have a company like Target that's been around 75, 80 years. People have worked there loyally for all that time to build it up as one of the great retailers in the United States. And one error could potentially bring a company like that down. This is very serious when you think about it. And here, one of the people have said, the Target breach is another wake-up call to the new threats in a connected world. Point-of-sale systems, that run this software are connected to the internet ultimately and open up vulnerabilities to attack from all over the world. Very serious problem. Another type of attack that has happened is represented by the fake Netflix app. This is a supply chain problem. As it turns out, new phones and tablets were shipped with a fake Netflix application in it. So it looked like it was the regular Netflix application, but an insider had actually put an imitation copy into the supply chain. And this, when users got their phone and activated their Netflix account, what they actually were doing was building a path from their phone or tablet to people in Russia who could read and receive all their credit card information that they entered on their tablet or phone. Now, as a consumer, when you buy a product like that, you sort of assume that at least in that initial state, everything is pretty secure and pristine. We know we need to watch out for attacks from the outside. But here's an example of an attack almost from the inside of the supply chain, that affected many users around the world who were not, it's not that they did anything wrong, it's just that they too naively accepted the fact that their data was going to be secure. I think that this was on more than 1 million tablets and phones that were shipped during that period of time. And I heard something the other day that was pretty interesting, another fact. It said that in 1998, there were 400 million devices with broadband connectivity in the world. And in 2012, just mobile devices, they had 1.2 billion devices connected broadband. So when we think about how many devices around the world are connected, not just these mobile devices, but industrial facilities, now some embedded devices and such, the attack surface is huge. The way people can enter into the system and affect all of us is getting very hard to handle. Okay? Another fact I heard was that as of last year, there were 9 billion embedded devices in the Internet of Things. Small things like maybe refrigerators that were communicating somewhat over the internet, or home heating systems that had internet accessibility. But that by 2020, just 6 years from now, they expect to have 28 billion internet-enabled embedded devices connected on the internet. 28 billion. So when you look at this, you start to say, well, how will we attack this problem? How will we make our systems more secure, more safe for our financial information, for our personal information, for our children? Or as I'm starting to learn more and more from my parents. My dad, my father, works on the internet sometimes. He's 86 years old, and I find his practices to be a little naive at times. He visits places he shouldn't visit, because they're just suspicious sites. He likes to read up about stocks on the internet, and he goes some strange places that I wish he wouldn't go. So we need to protect both our children and our parents and ourselves from the type of fraud that's on the internet. One of the things we know at SEI, and that we've worked on for 30 years now, is the fact that quality makes a difference in everything we do, in everything about software. Building high-quality code is cheaper in the long run. Building high-quality code is more secure in the long run. And building high-quality code is actually quicker in the long run for the life cycle of the system. We also know that software flaws tend to be introduced very early in the cycle, even as early as in the requirements phase itself. And yet often they aren't discovered until pretty late in the development cycle or even in operations. We also know that the later the flaws are found, the later the defects and bugs are found, the more expensive it is to fix them. You can imagine that once you get into operations and you have software deployed around the world, if you now find a flaw or bug that's severe, it's very hard to get that completely eradicated around the world. Not everybody's going to update their software when you tell them to update it, and there'll always be some attack surfaces where people can attack the whole internet through these vulnerabilities. Much of SEI's work over these 30 years has been to try to bring attention to this fact and to bring quality earlier into the system so that we discover the flaws early, that we learn from the types of flaws we introduce so that we don't introduce them again in the future, and that in a requirements and even architecture sense, that we think about the implications of the requirements and architecture early on before we just kind of willy-nilly, oh boy, that's not going to translate well, before we willy-nilly start writing code. Now we see many of these problems only getting worse in the next few years. We see major trends in software that I know you're seeing here in Japan as well. We're going to have systems that have more autonomy in them. And as we have more autonomous systems, the need for quality in the systems is going to increase. If we start to depend on systems to drive our cars, to fly our planes, to do other things in a more natural sense without human interference and control, we're going to have to be sure that these systems are more secure, more correct, less vulnerable to attack. So as autonomy comes, our need to ensure quality is going to increase. We also know that the systems that we're building are taking advantage of connectivity and increased complexity to do new functions, to bring new capability to the market that has never been seen before. This connectivity enables us to do some wonderful things, but it also, again, opens that attack surface. There's more chances for error. There's more of a need for high quality to reduce the possibility of compromise. We continue to look for, if we're going to have these much larger systems, how will we increase the productivity of our workforce to build these larger systems? How will we scale up? And there are techniques to do that we continue to look at, but this is very important. In a security sense, we know that we have to maintain code integrity, not only when we first build it, but throughout the operational life of the software, as we patch it, as we modify it, as we evolve it. We know more and more that the issues of securing the global supply chain are starting to become more important to us and more challenging to us as we move to a more global marketplace where we buy software and firmware and hardware from whoever makes it best all around the world. Even in US defense systems, they find that they're often buying parts now from China to go into US defense systems. And that opens up some interesting issues about the security of those parts and what might be in them. We know that we don't often start with a clean sheet of paper to design our systems. That most systems now are using a lot of existing code and building upon that. So we have legacy systems that have all the legacy problems in them. Problems may be introduced by software engineers 10, 15 years ago, and yet we're trying to put new capability on top of that that would also suffer from any security vulnerabilities that were in the legacy code. So how will we be sure that this legacy code is not going to have a catastrophic security flaw in it? The operational threats continue to grow, and we know that in the early days of the internet, there were a lot of hackers who were just doing it for fun. They were almost hobbyists. But now, it's much more professional out there. The criminals, cyber criminals, are much more organized, have a lot more money and a lot more training behind them. And the nations that do cyber attack have a lot of resources and a lot of capabilities behind them. So it's not just the hobbyists anymore that we have to worry about. And much of what we do depends on building and maintaining a very skilled and educated and up-to-date workforce. Around the world, though, in many of the first world countries, our workforce is getting older. We have less children growing into the workforce. And sometimes our children don't want to be engineers. They want to do other things. They're not ready to take on the difficult educational process that it takes to be an engineer. This is a big problem in the United States. I don't know if it's as big a problem in Japan, but in the United States, we don't feel like we're graduating enough engineers to even keep the momentum going for all the systems that we build. So what can we do about this? One of the things in a security sense that we are starting to push is that we really need to consider cybersecurity requirements at the very front of the development cycle. We know historically that often we've built the functionality of the system and only later in the development cycle tried to add on security principles. This does not work, and we've got the evidence of that around the world today. Security requirements are becoming some of the primary requirements of many systems. But often people don't specify security as well as they could. They say the system should be secure or maybe should have encryption, but they don't really say why they're doing this, to what level it needs to be done. They don't explore the requirements well enough to really give design level information to the architects and developers of the system. So we believe that we have techniques, and others have developed techniques, to explore these architectural concepts early in the development cycle, to look at the requirements and analyze them, not just accept them, but discuss them, analyze them, figure out where this is going to take the design early in the system. And the third item there, we feel like all of us, we have to think about how an attacker is going to attack this system. This gets back to the whole idea of thinking in a systems way. We have to think of how this is going to fit into the global infrastructure. What will this appear to an attacker, and how will an attacker try to take advantage of this? We believe that architecture is an extremely important part of security. So once you have those requirements identified, now you have to look at the architectural trades early in the program lifecycle to develop an architecture that will ensure security through the lifecycle. Sometimes this might come at the expense of other features you would like in the code. And we know classically that at times performance can be impacted by security. At times usability or ease of use might be affected a little bit by security principles. How do we make those trades? That is the issue for a great architect, system engineer, or software engineer early in the development of a program. You have to understand these things to such a level that you can make those trades so that you can guide your development workforce to building the software in the correct way. In addition to understanding the system qualities, we believe there are techniques now to better look at the trades early on through virtual integration, through modeling and simulation, techniques that we brought to the structural world many years ago with CAD/CAM operations and things like that. Now we're starting to bring modeling and sim to the software engineering world to enable us to look at these things much earlier in the life cycle of the software. This is very important, and I think is one of the future trends in software engineering. We know, having seen that data from the SANS Institute, that some of the security flaws that are out there are introduced because of the common software coding problems that have arisen over time. And these are things that we can prevent. So at SEI, working with the international community, we've had an effort over the last 15 years or so to develop secure coding practices. The leader of that group for us is a man named Robert Secord. And he's worked primarily in C, C++, and Java to develop techniques and instructions that would help people avoid the 20 to 25 most common security problems in each of those languages. It's not enough to tell people this, though. What we've tried to do now is to work with the international standards organizations to get this adopted in the international standards, and to work with the compiler community to develop automated checks to avoid these common software flaws in code that's developed when it compiles. It's a little harder to do that, but we feel like the only way to eliminate these defects on a very global basis is to have it as part of the compiler checks that go on. And one final thing, we've also developed sort of a test bed that in these languages of C, C++, and Java, we have code that can look at code and tell us if that code is compliant with the secure coding standards. So then we would have confidence that those common security flaws would not be in that software. Having done that, that's sort of on the very definitive side. We also have looked at various techniques developed around the world on safety cases and other ways to look at things that cannot be always proven exactly. And so we've brought some work from the University of York in England on safety cases to the US, worked on that and generalized it more to the whole idea of assurance cases. So how do we take code, hypothesize certain behaviors of it, and then start to collect evidence through test results, data, model checking, formal verification, to give us some feeling, some assurance that this hypothesized quality is actually contained in the code. This is becoming very important on the idea of mission assurance of software. How do we know that the software not only is not going to have defects, but actually will do the effort that it was designed to do. That it will actually meet the objectives of the program and not contain extraneous efforts inside there, such as malware. So we've worked for quite some time on how to do this, and we've got instructions, methodologies, techniques to help people gain better confidence that the software is going to meet its mission needs. Much of the world has gotten more and more involved with the ideas of agile development practices. And many of the principles of the Agile Manifesto are very good, rational type assumptions. If you read the Agile Manifesto in total, you'll see that it often says we believe in all things, but these things more. You know, we believe in working code more than documentation. It's not that they don't believe in documentation at all, but they believe that working code is the ultimate artifact that you need for a software development. What we found, though, is that in many of the early instances of agile development techniques, people don't pay much attention to architecture early in a program. This is not really catastrophic on small developmental efforts, where an individual programmer or a small team sort of has an architecture in their mind even as they start. But we found that this does not work very well for national class software, global class software, software that has to be developed by teams of 100 to 400 to 1,000 people. Software that has so many functions in it that it's not intuitive what the architecture would be. And so in many of these systems, what the Agile community has found is that as they write software in these early sprints, in these early cycles, in these early launches, they get working capability. But then maybe a year into the overall development, as they start to add some new feature, they find that they've gone down a path that has led into what in the United States we'd call a cul-de-sac. They've come to a place where they can't really progress without going backwards for a while. This is the concept that we call technical debt in the United States. That you've gone down a path that looks good and you've gotten great capability, but all the time that you were doing that, you were moving away from the ultimate goal of the major system. Another example of not really having a systems view as you begin the development of a program. We believe the answer to this is to figure out what's the right amount of architecture to have in an agile program early on. I was originally trained as a physicist, as was my friend Akiyama-san, and I have lots of quotes from physicists that I think about. And one of them was from Albert Einstein, who once said, "A theory should be as simple as possible, but no simpler." Very profound when you think about it. An agile developmental program should have as little architecture as needed, but no less. So you need to have some architecture to guide this larger development effort over these many years that you might be developing a big system, such as an air traffic control system, a global finance clearing system, or something like that. Okay? So what we found is that agile techniques often end up with code that's a little hard to maintain because it really wasn't built with the idea of maintenance in it at times. And they end up with these suboptimal architectures that require people to go back and redo code that they've already developed. And whenever you redo code, whenever you redo effort, you're actually wasting effort and not really being agile in a sense. Okay? So we try to work on techniques that make this technical debt more visible earlier and associate it with risk, and try to find ways to bring in enough architecture to actually make this technical debt smaller as we go. Another technique that we're very excited about gets to this whole point of virtual integration of software. I mentioned already the structural business. Airframe manufacturers build exquisite models of their airframes before they ever bend metal. Okay? We need to do the same thing in software now. The complications that we tend to run into when we integrate large pieces of software have shown that we need extra help. And various communities, even programs as simple as MATLAB help you with this. in the way that you can look at a program early on and see what might be developed. We've done some work with the aerospace industry in the United States, looking at techniques to take the airframe manufacturers, along with the airframe and the engines, and work with the avionics community, the people building all the electronics that goes into airplanes, and to virtually integrate this electronics very early in the design cycle to see the trades that need to be made to make sure you're going to have the performance that you want. The technique that we've worked on is called the Architecture Analysis Design Language, AADL. More information about that's on our websites, and we can certainly share that with you. There's some books written on it as well. This has been adopted by Boeing and Lockheed and Rockwell Collins and the major manufacturers in the US that are involved in the aerospace industry, and being used by the government in some new helicopter programs at this point. It's also gotten some adoption by OMG, the Object Management Group, which is building some extra tools to go along with this. So you may be able to get some extra help on this from which we've done in the past. I mentioned the issues of supply chain early on. These are risks that are going to be harder for us to handle. Software engineers in particular have not usually worried so much about the software, the firmware that's coming from vendors. But now as we see when we integrate these things into our systems, these new components that we might buy, we're bringing in risk. And part of our job is to balance and minimize the risk to our systems. In the past, we've had some cases where firmware, programmable gate arrays, even hard-coded integrated circuits have contained malware that was entered at the source, was designed into the chips. So it wasn't malware that was in software, really. It was malware that was in hardware. And some of this hardware has reported valuable information across the internet to the originators of that work. We're looking at more and more techniques for how we can run tests against procured hardware and software to understand if some of the common vulnerabilities and malware are in these systems. Getting back to the drum about the system, we've found that it's not enough for the software engineers to be concerned about this. Not enough for the system engineers to be concerned with this. That in reality, we need everybody involved in the program to be thinking about the software issues that are out there, especially cybersecurity. And so we're preaching more and more to people that managers in organizations, up to the CEO and the boards of companies, need to be much more aware of the fact that many of their companies, they might think they're hardware companies, but in reality, they have become software companies over the ensuing years. I mentioned the case of Amazon already, and Amazon is really a software company. But now when you look at Boeing, Lockheed, Raytheon, they're largely software companies. When you look at JP Morgan, it thinks it's a bank, but it's run on its software. And if the software fails, the bank could fail. In the US, there's actually legislation right now requiring the boards of publicly traded companies to consider the cybersecurity risks to those organizations. And in many cases, the boards of these companies really don't have the people sitting on them with the right skill set to even think about this. I think this is going to be a trend across the world as people start to understand the damage that can be done from a cybersecurity problem. They're going to want at least somebody on that board who has this technical savvy, the technical capabilities to consider the risk that is occurring to that company, just as we've done with the financial savvy that needs to sit on boards of directors around the world. I really believe that we've come to the point where some software skills are needed in almost all jobs. It's not that every person in the group has to be able to write code, because we'll never get to that point. But we do believe that people in various organizations and various positions have to be aware enough of software, what it can do, what it can't do, what the risks are, what the problems are, that they can be good members of the management team in looking at software. In my Air Force days, we felt that program managers of Air Force programs really had to have engineering insight to be able to manage the complex programs that they had. It didn't mean they had to be engineers per se. They didn't have to, have graduated from college as a mechanical engineer or whatever. But they had to have accrued enough engineering insight from their on-the-job performance and from continuing education during their development as engineers, as managers, to understand the sensitivities and risks that were there, so that when they were called upon to make big decisions in their program, to balance trades about schedule and cost and technical performance, they could do that in a good way. I believe now, in the 20 years or so since I was a program manager in the Air Force, this has become even more important, and especially with respect to software. Many of the program managers that we have in the United States, I would guess in Japan, have arisen through more traditional engineering disciplines, mechanical, electrical, aeronautic. We have to have people in management that also understand software engineering if they're going to make the good decisions. In many of our systems out there now, 80% of the functionality is resting in software. When you talk about a software reliability center, we know that here. We have to make sure others understand this throughout our countries and throughout our industry, that the software is the key to much of the way the system performs and its security and reliability. Some things we know about our workforce. We need to think about the business cases when we're adding new features to software. We need to be careful about how much we add and when we add it. We know we have to secure the supply chain. I think we've already made the case a little bit about insider threat, and I'm going to talk about that a little more on one more slide. We know that management and everybody in the workforce has to understand systems behavior better than they did in the past if they're going to balance and make the right decisions. And we know that velocity, this is supposed to have agile with a little a, not agile with a big A, that the velocity of development is really important in this cyber era, that bringing things to market sooner is often the difference between success or failure. So if we want to have velocity, we have to find ways to build secure, safe systems, but in a quicker way than we did in the past. One thing that we believe is true, and I think is understood in Japan and other first world countries, is that the cyber environment is changing so fast, the technical methods and details are changing so quickly, that it's very important for all of us to be involved in continuing education. As I mentioned earlier, I graduated from college in 1972 with my undergrad degree. The computer world was very different in '72 than it is now. And this, if you really look back even 10 years ago, the kind of systems we have today are very different than they were 10 years ago. In the social media side of things, companies like LinkedIn, Facebook, they didn't exist 10 years ago. They've all been recent phenomena. One of the interesting articles that was written in the Wall Street Journal about 3 years ago by Mark Andreessen, who was involved in the development of Netscape, was called "Software is Eating the World." And the point that he was trying to make is that when you look at all the great companies that have arisen in the last decade, at their heart, what they brought to the table was a good understanding of how software could help them scale their operations, could help them bring their operations to the world or do it in a larger, cheaper way. And he was talking about Amazon and FedEx and Walmart and other companies like that have really understood how to operate globally in a big way. So we all need to continue our education as we work in our careers over 40 years or more. When all is said and done, no matter how secure we make our systems, we know that they will be violated, that ultimately there will be some penetrations. And so just as the human body works even when we're under attack through a disease, we have to build systems that are resilient enough to work even when they're under attack, even when they have been compromised to some degree. There are techniques to do that, and some of them have been pioneered in the past by making companies resilient to even natural disasters, to understanding how we can survive typhoons or hurricanes in the US, how we can survive earthquakes and natural disasters and have our company continue to exist. It does no good to a company if a natural disaster happens or if a software disaster happens, if they have to shut down for a month or a year or even go out of business. We want our companies to be resilient. We want our governments to be resilient. We want our governments to be able to provide emergency care to people when there's natural disasters or when there's cyber disasters. Part of the idea of resiliency is to find ways to isolate the damage, the penetration, and reduce the cost of recovery, to bring the organization back to full speed as fast as it can, so it can continue to earn revenue and do the mission that it's supposed to do. There are lots of techniques for that. We've worked on that through something called the Resiliency Management Model at the SCI. It doesn't look just at software. It looks at the overall issues of continuity of operations for an organization. And I want to talk just a few seconds about insider threat. At SCI, we've done work over the last 10 to 15 years on insider threat, and found that this is maybe one of the more severe cyber threats to any organization. We've looked at over 1,000 cases of insider threat in the United States, and I have to caveat my comments by saying that all the cases we've looked at were US cases so far. We've done this in cooperation with law enforcement officials in the United States, such as the FBI, the Federal Bureau of Investigations, and the Secret Service. Because we've worked with them, in all of these cases, we've had access to the people who collected the evidence, who prosecuted the criminals. And in many cases, we've been able to interview the criminals that have been convicted and put in jail, to find out why they acted the way they did, what was their motivation, what they thought. What were they worried about is maybe tipping their hand that they would be discovered. We found that there's 4 general cases of insider threat that each have their own characteristics. One of them is kind of obvious, and that's the national security espionage type of insider threat, represented by our friend here, Ed Snowden, who's caused a lot of trouble to the United States around the world. But in an industrial sense, there are 3 other types of insider threat that are important, and each have their own characteristics. Each of these can bring down a company, and we've seen companies brought down by insider threat. The first case is exemplified by Gillette, which builds razors in the United States. And this is the theft of intellectual property. There was a process engineer working for Gillette in Tennessee who stole 600 megabytes of intellectual property from Gillette, gave it to one of their competitors because he was upset that he'd been passed over for a job, for a promotion inside of Gillette. Fortunately, he was caught before the competitor was able to use this information and convicted, and Gillette was able to recover that information before it became public knowledge. But it shows that, you know, a company like Gillette could spend a lot of time and money perfecting a product that they hope gives them a marketing advantage in the business world. And in one instant, with one USB drive, you can take so much information out of a company that you could bring that company down and make all their investment in that research meaningless. The middle picture here is of Aramco in Saudi Arabia. And there was a case there of what we call an insider threat through sabotage. An engineer was very upset with some of the goals of the company and brought the operation down of Aramco for almost 20 days a couple years ago by sabotaging their IT systems. This is a little more common when people are leaving a company, because they usually don't want to be at that company when this happens, or who are really upset about something that happened to them in the company, like a promotion they thought they didn't get, that they weren't being, maybe getting the raise that they thought. But IT sabotage has actually caused a few companies in the United States to go out of business because they were out of operation for so long that they weren't able to recover. And then the final example here with Visa is the classic one we think of IT, insider threat, and that's through fraud, through finding ways to actually take money out of the organization by an insider. Insiders finding ways to divert money to themselves, to their families, to their friends, so that they can have a benefit. So we've seen in the industrial sense 3 major types of insider threat: theft of IP, sabotage, and fraud. And we've developed sort of event trees for each of those types of threats, for what the indicators are and how they might be prevented in the various companies. One of the things that's become important to realize is these are not just going to be solved through technical means. These are, you can't just run a program on your inside networks to see if an insider's doing something bad, because many times the insiders are actually authorized access to some of these regions of the internet. So what you have to do is integrate not only the technical means you have of observing what's going on inside your company, with some of the non-technical means, such as your HR department being aware that if they're getting ready to terminate somebody, maybe we better be a little more careful about what's going on. If people start to understand somebody in the organization is having a lot of stress on them for various reasons, better understand that stress and start to examine how's that affecting the person? What is the person doing that might be different than they've done before? So we have to bring the technical means along with the human resource means to really prevent insider threat. And in the United States today, I guess we don't have this on here, there's a new requirement that people have, companies are going to have insider threat programs if they're federal contractors. I want to close with just this, these few summary items. First of all, we know that there's cybersecurity problems out there in the workforce, out in the installed base of software. Unfortunately, often we don't see them, we don't detect them until they're in operations and until they've already had an impact on us. Too often we're finding we scan for security problems after we've seen an attack and know what to look for. We have to start to get ahead of that curve. We know that the vulnerabilities in software caused by common programming errors are often the entree point for cyber attack. We're convinced we can build better systems that are more secure, that do their mission more assuredly, by focusing on software quality throughout the development cycle. We do that not just for the abstract reason of quality, but because it makes a difference. It causes systems to cost less, it causes them to be more secure, it causes them to be developed quicker, and to have longer lifetimes. And we think all organizations have to recognize that they are becoming software organizations, and they better think about the fact that all organizations ultimately are software organizations. Now this has implications, as we mentioned, to the managers, to the business developers, to the board members, even the people that are not on the technical staff in companies, that they have to understand software. I think it's my last slide to see. Yeah, so let me just end on this slide, but say something else that I think is really important. This is a global business. No one organization can take all these problems on by themselves. We operate in a collective way now around the world. So it's very important that all of us work to improve the capabilities of software around the world. We do it often because of our countries, because of our companies, but we also need to do it because it's the right thing to do for our global software engineering community. We need to raise the baseline all around the world. The only way we can do that is to collectively work with the smartest people around the world, with the most passionate people around the world. And as my friend Jim Over always says, that we actually have data to base our decisions on our development techniques. We still need more data in this business to make sure we understand how software is being built and what the best ways of building software are. That's something we need to collect from the global software engineering community, not from any one country or one organization. So we need your help. And I think we've found over the last years that SEC and SEI have a lot of common grounds that we would like to work on. And I think the development of data in this area and the analysis of data in this area is one way where we could really work together much better. So with that, I'd like to close and see if we have any questions. I guess I have maybe a few minutes for some questions. And I want to thank you again for paying attention to me. You know, they always say the speaker, it's really bad when the speaker doesn't stop talking until after the people stop listening. We want the speaker to end before the people stop listening, basically, and that's true. And I was very happy to do this. I know it's very hard to listen to someone speak in a different language, and to do this simultaneous translation is a real challenge for the translators and for the people listening through these devices. So I want to thank the translators for their excellent work, and hope that you have some good questions for me.
どうもありがとうございました。
Thank you.